Hey guys, this is 6.3. 6.3 is about exponential functions, and you may be thinking, we know exponential functions, x squared is an exponent, x cubed is an exponent, right? But an exponential function is not only a function with exponents, it's a function where the exponent, the variable is in the exponent. So you would have the one we're going to work with first today is just 3 to the power of x. Okay, so we're going to learn how to graph these. We're going to learn one way to solve when the exponent is in the, when the variable is in the exponent. And then in the next class, we'll figure out how to solve if we have 3 to the power of x equals 10, we will figure out how to solve that. Okay, so this is building up to 6.4, where we will work on logarithms. So let's get started. Hopefully that's in focus. So an exponential function is a function with a variable located in the exponent. Okay, it's not only that it has an exponent, but that it is located in the variable is in the exponent. So x is obviously our variable and our exponent. I am sure you have heard that if you have an exponent, you also have a base. So a is our base. Our base could also be called our growth factor. Because it shows how quickly it is growing. Okay, and then C is our initial value, what we are measuring. Initial means first, right? Initial value is C. Exponent is X, and the base is A. The domain of this function is all real numbers. The base is the growth factor, and C is the initial value. Yeah? Okay, so we're going to learn how to undo a to the x. Okay, how to solve for x. If we had 2x equals 5, I wouldn't really know what x is or how to find it, right? But by the end of 6.4, you will know. So this is just to get you familiar with this half of the equation, okay? So we're going to be comparing exponential growth to exponential decay. They're very similar, okay? The domain of a graph of exponential growth is all real numbers. So the x values go from negative infinity up through infinity, okay? The range is only the y values. And if you can see, the y values move toward y equals 0. They will never touch it and they will never cross it. So the range is all positive numbers beginning after 0, right? Because this isn't a bracket, this is a parentheses. So beginning after 0 and moving toward infinity. There are no x-intercepts because it never crosses x. And the y-intercept is 1 because any number, so we're working with, as we already pointed out, we're working with a to the power of x, right? So this point is 1 comma a because whatever a is, let's say a is 13, okay? 13 to the power of 1 is 13. So x is 1, a will be 13. It looks like a is 2 here, right? 1, 2. So 2 to the power of 1 is 2, but either of those to the power of 0 is 1. So that's why they will always have a y-intercept of 1, this point will always be on a graph of exponential growth, because no matter what a is, if you raise it to the power of 0, the answer will be, sorry, if you raise it to the power of 0, the answer will be 1. Okay. The x-axis y equals 0 is a horizontal asymptote. It will never cross the x-axis. If you look to the far left, the graph is approaching y equals 0, and it gets closer and closer and closer and closer and closer with every point, but it will never touch y equals 0. And it is an increasing function, and it is 1-to-1. Increasing means it is rising, it is growing. And 1-to-1 means if I perform the horizontal line test, it'll only ever cross this equation's graph at a single point. Every horizontal line I put across it will only touch it at one point. Okay. It's exponential growth. It's growing because it goes up from left to right. A is how fast it is growing. All right. If a is greater than 1, it is exponential growth. And then it's going to give us an example of exponential growth. Okay. So it has all the attributes from the slide before. I know it's growing from left to right. I know it'll never cross x. I know it'll cross y at x equal, or sorry, it'll cross y at 1 when x is 0, right? But that's kind of all I know, and I need more details. So the way I get details if I'm about to graph something is by creating a table of values. So I'm going to make a table of values right here. It will include x. So when I put in an x input, what will I get out? Y equals 3x, right? What will y be? Or what will f of x be? And then what will my ordered pair be? Okay. And I just want simple x's so that I get a good idea of what the graph is doing, but I don't have to make my graph too big. So I'm going to go -2 to +2. -2, -1, 0, 1, and 2 will be my points, my x values for my ordered pairs. And I'm just going to plug those into 3 to the power of x. So y will equal 3 to the -2, right? 3 to the -2. I'm gonna, what do I do if I have a negative exponent? If I have 3 times itself -2 times. Remember, if you have a negative exponent, you can take that whole thing, move it to the other side of a fraction, and it will turn positive. So now, sorry, we don't have a 3 on top. We have a 1 on top, and we have the 3 on the bottom, and now that -2 becomes a +2. 3 squared is 9. So 3 to the power of -2 is the fraction 1/9. So when x is -2, y is 1/9. When x is -1, you might be able to see where this is going. Same thing, but now I have -1. 3 to the -1st power over 1. I'm going to flip that to the other side of the fraction bar. Now I have a 1 on top, 3 to the 1 to the 1st power on the bottom. Anything to the 1st power is itself, so it's 1/3, okay? So when x is -1, y is 1/3. When x is 0, we just talked about that, 3 to the 0 power is 1. So when x is 0, y will be a +1. When x is 1, 3 to the 1st power, we just did it over here, 3 to the 1st power is 3. So when x is 1, y will be +3. 3 squared is 9. So when x is 2, y is 9. All right. So now we have some points that we can use to graph this function. I'm only going to have positive y values for this graph because I know that it will approach that horizontal asymptote y equals 0. And I only have +2 and -2. So I'm just going to go out 1, 2, 1, 2. So this is -2. This is +2. I know I have a 1/9 and a 1/3, so I'm going to kind of make these bigger. Good. All right, so when it's -2, y is 1/9. That's very close to 0 comparatively. When x is -1, y will be 1/3. It's closer to 1, but not very close. When x is 0, y will be 1. When x is 3, y will be 3. And when x is 2, y will be 9. So there is my graph of the exponential function f of x equals 3 to the power of x. And I'm just going to make a smooth and continuous function line right here. Then I'll make my points bigger so that they actually are covered by the line I drew. Remember, it's never going to touch 0. So even though that looks very close, with each number coming out, it will get closer and closer. It will never touch 0. All right. Oh, let me find it in Desmos. I'm going to pause 1 second. Yes, I had it. All right. So in Desmos, I don't need all these. I just need 3x. All right, so it crosses y at 1. It approaches 0, but it will never touch. Sorry. All right, back to Desmos. So we saw that at -7, it looked like it was at 0, but it's just because we didn't zoom in far enough. So as the decimal gets smaller and smaller and smaller, it's harder and harder for Desmos to show it, but notice that it does not ever become actually 0. So we could go as far out as we wanted, like to negative, I don't know, 28. And if we zoom in really, 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 really far, zoom in so far I can't find it. Okay. Again, share screen, Desmos. All right, I zoomed in far enough. And you can see that -27.597, which had originally said was (0), it's actually (6.806 times 10 to the -14. So you just have to zoom in really far to see that it's not 0. It's just very, very close to 0. It will never actually become 0. So the graph is moving closer to 0 towards the left, and towards the right, it's going straight up. And it's rising exponentially, 0, 1, 2 to the 2, 3, sorry, 1, 3, 2, 9, 3, 27. It's growing exponentially, okay? And that follows our graph that we made. Now we're going to contrast that with exponential decay. Exponential decay is falling, if you can see, rather than rising, right? The base is between 0 and 1. That is how you define exponential decay versus exponential growth, because growth is going up, decay is going down, right? Base between 0 and 1. So it would be a fraction or it would be a decimal. Similarly, the domain is the set of all real numbers. The range is all positive real numbers. There are no x-intercepts. The y-intercept is still 1 because we're still raising it to the power, and raising it to the power of 0 will always give us 1, even if it's a fraction or a decimal. There are no x-intercepts. The y-intercept is 1. The x-axis is a horizontal asymptote, so it will never touch 0. It will just get very, very close. It is a decreasing function, and it is 1 to 1. If I perform the horizontal line test, I would only ever cross the graph of this function at a single point, and it is smooth and continuous. I'm not picking up my pen. All right, so let's now graph the exponential function of decay, 1/3 x. So the other one was 3x. Now we're at 1/3 x. What we need to know about 1/3 x is that the base, 1/3, is between 0 and 1. Okay? It represents decay because 1/3 is between 0 and 1. So I'm going to again use a table of values to figure out how best to graph this graph of exponential decay. So I'll have x. I'll have y equals 1/3 x. And I will have xy, or my ordered pair. And I'm going to use the same x values. I have a -2, -1, 0, 1, and 2. Okay, so when x is equal to -2, what will y be? And y is 1/3 to the power of -2. 1/3 power of -2. And last time when we had 3 to the power of -2, we made it into a fraction and we moved it across the fraction bar, right? So I'm going to do the same thing. So now it's 1/1/3 squared. If I want to square a fraction, all I do is square the top and the bottom. 1 squared is 1. 3 squared is 9. 1/1/9 can also be written as 1 divided by 1/9. Since that's a fraction, I'm going to turn this into a fraction. It's 1/1, right? 1 divided by 1/9. We're going to keep, flip, change it, right? So keep 1 to 1, flip 9/1, change the division into a multiplication and multiply straight across. 1 times 9 is 9, 1 times 1 is 1, so 9/1 or 9, okay? You're also welcome to use your calculator. 1/3 to the -2nd power is 9. So where x is -2, y is 9. When it is not -2 but -1, we do the same thing. 1/3 the -1st becomes 1/1/3 to the 1st. 1/3 to the 1st is just 1/3. So that's 1 divided by 1/3, right? Just wrote it horizontally instead of vertically. So that's 1/1. Keep, flip this. So turn the 3 upside down, the 1 on the bottom. Change from division to multiplication. 1 times 3 is 3. 1 times 1 is 1, 3. So 1/3 to the -1st power is 3. Anything to the power of 0 is 1. So 0, 1, just like every exponential equation. Where x equals 1, y is going to equal 1/3, right? Where x equals 2, we already did that here. 1/3 squared is 1/9. All right, and I am ready to graph. You might notice how similar it looks to that first graph we did. All right, keeping it all above y. All right, at -2, my y is 9. At -1, my y is 3. At 0, my y is 1. At 1, I'm at 1/3. And at 2, I'm at 1/9. And just like in Desmos with the last one, each time we're going to get smaller and smaller. So this was 1/9. This was 1/3. This would be 1/27. This would be 1/81st. Yeah, because we're dividing by 3 again. Divide 81 by 3, I get 243. So that's 1/243. This would be 1/729. So we're getting smaller, we're dividing by 3, but no matter how long we divide, so I have 1, I divide it by 3, divide that by 3, divide that by 3, divide that by 3. I could do this, oops. I could do that forever. And I would never get to 0. I would get to where my calculator might even call it 0. But do you see how they start using this now? Very small number, just like Desmos did. It will never be 0. It just gets closer and closer and closer. Good. So here's our graph. Our graph is falling. So that's good. Because it was supposed to be a decay, because 1/3 is between 0 and 1. Ooh, I already crossed x. We never cross x, we cross y at y equals 1. And it goes forever in both directions on the x-axis. So let's look at our Desmos equation for this. It crosses at 1. -2 gives me, my goodness. -2 is at 9. -1 is at 3. One is at 0.3. 2 is at 0.1. So that follows our graph that we have. It's just much more beautiful. All right, so now we are using transformations like we used in the last unit, okay? My parent function for this graph is y equals 3x. And here is y equals 3x, okay? And to that function, we are going to add 1, and we are going to make that x into a negative x. All right, what will that do to this parent function? What transformations were applied? So first of all, the x is being multiplied by a negative. So a negative x means that when x is multiplied by a negative, the parent function is reflected across the y-axis. Reflection across the y-axis. Why would this be true? So here, my x is 2, right? If I made that into a -2, instead of being 2 positive, I've changed it to 2 on the opposite side. This is a 1, 3. If I made just the x's into negatives, it would become a -1, 3, right? +1, 1/3. The opposite of that, or sorry, -1, 1/3. The opposite of that is +1, 1/3. -2, 1/9. The opposite of that is +2, 1/9. So all of my x's have changed places because I changed them to their opposite. And what that does is reflects it or makes it a mirror across the y-axis. All right. The second transformation is that we added one. We didn't add one to the x, we added one to the entire function, or to kind of to the y, right? And remember, when you add or subtract, those are shifts. If you add and it is grouped with the x, that would be a horizontal shift. If you add and it is not grouped with x, that would be a vertical shift. The plus means it goes up, right? So it's a vertical shift up 1 unit on the y-axis, which is kind of redundant because the y-axis is up or down. So we're shifting up and we're reflecting it across y. So now the 2 became a -2, the 9 became a 10. Yeah. The 3 became a 4. The 1/3 became a 1 1/3. The 1/9 became a 1 1/9. So now my points are, here I have a -2, 10. Right here. Here I have a -1, 4. -1, 1, 2, 3, 4. Here I have a +1, 1 1/3. Here I have a +2, 1 1/9. Oh, sorry, that goes to 2. We have a 0, 2. Because we moved it up 1. So that is my new graph. We've reflected it across the y-axis and shifted it up 1. The horizontal asymptote is now at y equals 1 instead of y equals 0. So now it will be constantly approaching 1 instead of constantly approaching 0. Closer and closer to 1, it crosses at 2. It crosses -1x, give me a 4 on the y. So that matches my graph. This next slide tells us about the number e. So beyond college algebra, you will encounter things called limits in calculus and those courses. E is the limit. So how we read this is the number e is defined as e is the limit as n approaches infinity of the quantity 1 + 1/n raised to the power of n. It also has a numerical value that we can approximate as 2.718281828, etc. It's in your calculator, kind of like pi is a number and it's in your calculator. On a TI calculator, it should be above your division. Or sorry, it should be your division button, but after you hit second, and you get 2.718281828. Good. So if we wanted to graph the equation f of x equals e to the power of x, we would need to calculate each of these, right? And it would be a graph of, since it is 2.71, that is greater than 1. So that is growth. The negatives are small. 0 is equal to 1, and the positive x's are growing larger. So that also fits with a growth, exponential growth. And then when we look at the graph, it is also a graph of exponential growth. Good. And E is, yeah, it's just something that you will encounter more and more often as you get into higher math. So we're going to use E to graph the next transformation. F of x equals negative E of x plus 2. This is my graph, my parent function of y equals e to the x. I'm very bad at approaching these asymptotes without crossing them. Please know that they should not be crossed. So there are two changes we're going to do to the parent function. We are going to make the e a negative. So a negative e instead of a negative x, right? Last time we had a negative x, which reflected across the y-axis. A negative e makes the whole equation negative, so we have reflected across the x-axis. Because the whole equation is your y, right? You put in an x, you get out a y. So now I'm changing my y's from e squared to a negative e squared. So that has to go all the way down to 9. From a e to a negative 2-ish, right? 2.7. 0 to 1 becomes 0, negative 1. 1 over e, negative 1 over e. 1 over e squared, negative 1 over e squared. So we're reflecting across the x-axis because we changed all the y's. Good. And then our second transformation was we added 2 to the x. Remember, when we group it with x, it's a horizontal. And it's an addition, so it's a shift, but it doesn't shift in the way you think. Horizontal on the x, you would think a positive 2 shift would move it to the right, but it doesn't. Remember, horizontal shifts do the opposite of what you think they will do, so it becomes a negative 2. So to the left 2 units. So now I have transformed this across the x-axis. Now I move it to the left 2 units. So instead of 0, negative 1, or let's start here. So this negative 2 becomes a negative 4. The negative 1 becomes a negative 3. The 0 becomes a negative 2. The 2.7, or the e, becomes a, the positive 1 becomes a negative 1, and the positive 2 becomes a 0. So now this is my graph. And let's check it. Ignore that. Let's check what Desmos would say. Where did they have it crossing? They were crossing at -7. That looks good. All right, so we reflected it across the x and we shifted it over to the left by 2. Looks good. Our last page, no more graphs. You have finished graphing. That was very difficult. You did great. All right, this is just for solving for exponents if you can, okay? The first tactic for solving for, if you have a situation where you have exponents and you don't know how to get them out of being exponents, I guess, right? Like if I was multiplying, I know that the inverse of multiplying is dividing. I know that the inverse of adding is subtracting, right? There are lots of things I could do. If it was not in the exponent, but it had an exponent, I know I could do this, right? But I don't know what to do when the x is actually up here. So this is the first thing you can do. You can use the rule of exponents. If you have an equation and the base on the left is equal to the base on the right, then the exponent on the left must equal the exponent on the right, okay? If the bases are equal, the exponents are equal. If the bases are the same, the exponents must be equal. Right, so that sounds kind of obvious, like x to the 5th equals x to the 5th, right? Or x to the 5th equals x to the y must be 5, right? But you can use this to solve things that are a little bit more complex than that. Solve each exponential equation. So here we have a base of 2 with an exponent of x plus 2. Here we have a base of 8 with an exponent of understood 1, right? Is there a way to use this rule to solve for this x? Yeah, it says rewrite the sides to contain the same base. Good. So right now, one of the bases is 2 and the other base is 8. I know that 8 is, let's do a factor tree. 8 is 4 and 2, right? 4 can become 2 and 2. Keep that 2 the same. 2 times 2 times 2 is 8. So 8 is 2 to the 3rd. 2x plus 2 equals 2 to the 3rd. Now my bases are the same, so I can get rid of the bases and just say x plus 2 is 3, x is 1. Good. So for that one, we manipulated one side of the equation. We manipulated the 8 to turn it into the 2. If we look at this, we have a 9 and a 27. I can't really manipulate 27 to make it 9 to the power of something, right? Because 9 to the first power is 9. 9 to the second power is 81. That's quite a jump. It never hits 27, right? But we can try to find something they both have in common. What number can be raised to a power to equal 9 and also raised to a power to equal 27? Well, the only factors of 9 are 3 and 3, right? So I'm going to say 3 squared. And I'm going to say 3 cubed. Now I'm going to, we know that a base raised to a power raised to another power is multiplied, right? That's the rule of exponents. So I'm going to distribute that 2 to the 2x minus 5. 2 times 2x is 4x. 2 times a negative 5 is negative 10. 3 to the power of 4x minus 10 equals 3 to the power of 3x. So now we have the same base, and we can get rid of the base and just set those two exponents equal to each other. 4x minus 10 is 3x. Good. I'm going to put all my x's on one side. So I'll subtract 3x. Four x minus 3x is just x minus 10 equals, now it's 0 over here. I'm going to move that 10 over and I'm going to say x is 10. Ooh, and excuse me, I forgot. we can check these. So 2 to the power of 1 plus 2 is 8. All right, this one is 10. So now we have 9 to the power of 2 times 10 minus 5 is a very big number. And then 27 to the 10th is that same very big number. So those work out. Our final bit of work for today has e to the power of negative x squared equals e to the power of 5x times 1 over e to the 6th. Okay. It looks complicated, but I think we can simplify it. Specifically, I think we can simplify this side. So I'll just write e to the power of negative x squared. Wow. A power within power is e to the 5x times 1 over e to the 6th. I'm going to change this into a fraction and just multiply it straight across. E to the 5x times 1 is e to the 5x. 1 times 6 is e to the 6th. Sorry, 1 times e to the 6th is e to the 6th. Good. I know, just like rule of exponents here, I said they multiply. Rule of exponents here is we can subtract them if the base is the same. So now I'm going to say e to the negative x squared is e, and instead of a fraction, I'm going to say 5x minus 6. Now, if you'll notice, we have the same base, so I'm going to get rid of the base and just say negative x squared is 5x minus 6. If I have a squared and I have 1 to the 2nd power and 1 to the 1st power and 1 to the 0 power, that looks like a quadratic equation, right? We can use the quadratic formula to solve it, or we can factor it. First, let's set it in, put it into standard form. So I'm going to say 0 is, because I want my first term, my leading term, to be positive. 0 is x squared plus 5x minus 6. Good. Do you think you could factor this? 0 is, we have an x squared, so that factors into x and x. We need 2 terms that multiply to negative 6 and add to a positive 5. That would be negative 1 and 6, positive 1, negative 6, 2, negative 3, or negative 2, 3. Which one of those would add to a positive 5? That first one, right? So x minus 1, x plus 6. Now I set each of those equal to 0. 0 equals x minus 1, so x is 1. 0 equals x plus 6, so x is negative 6. Good, and we can check the. All right, let's check our answers. So we have x equals 1. E to the power of 1, so that would be a negative 1 squared is 0.367879. And then e to the power of 5 times 1 multiplied by 1 divided by e to the 6th. Same answer. All right, so we know that that checks. Negative 6. I'm going to put a negative 6 in here. I'm going to put a negative 6 in here. That one checks. All right, and that was And that was your introduction to exponential functions. Thank you guys so much and see you next time.